notes. So we're doing notes on pitch, frequency, and intensity. So we're going to deal with how different waves sound, and then we're also going to talk about how loud they get. And I have some demos that I'm hoping work, maybe. I've been fighting with them all through the week, trying to get them to work, and they're not working great. So we're going to keep trying, and hopefully we'll get some decent stuff out of it. So, pitch, frequency, and intensity. Now, some of this is also going to be a review from last time when we talked about waves, and some of it's going to be new or expanded upon. So, pitch and frequency. The particles of the medium through which the sound moves is vibrating back and forth in a back and forth motion at a given frequency. So when we look at frequencies, it's how often the particles of the medium vibrate when a wave passes through them. And so I have a number of different tuning forks. And so when I tap the tuning fork, it vibrates at a specific frequency. And everything that's a solid, liquid, or gas all vibrate at very specific frequencies. We call this a natural frequency. We're going to get to that later. But an example might be like a guitar string. Okay, a guitar string vibrates at 500 hertz. So when you pluck the guitar string is actually moving back and forth. And as it does that, it moves the air particles around it back and forth. And by doing that, it creates a compression wave. And so those compressions move, and then they move the particles next to them, and they move the particles next to them, and that sound transfers to your ear. Okay? So a guitar string vibrates at 500 hertz. It sets the air particles in the room vibrating at the same frequency, and then you hear the 500 hertz sound, which carries a sound signal to the ear of the listener, which is detected as a 500 hertz sound wave. Now, when you guys played with the instruments you guys made across the table, when you actually pluck the string on the table, which is similar to the way a guitar works, you guys basically made a guitar on the table without the resonant chamber. What did you notice when you guys looked at the frequencies? Was there one, or is there like all over the place? They were all over the place, okay? There's like multiple frequencies going on. And there's a reason for that. When we vibrate things, they don't always vibrate at one frequency. There's multiples. It's pretty rare for something to have a pure sound. Tuning forks being one of the few exceptions. They generally vibrate at only one frequency, okay? But we're going to talk a little bit more about that next time. Today, we're just going to talk about pitch and frequency. So, human perception of sound. The human ear is capable of detecting sound waves with a wide range of frequencies, ranging from about 20 hertz to 20,000 hertz. Anytime we encounter a sound that's below that, we call it infrasound. Okay, so below 20 hertz or so is infrasound. They're just sound waves we can't hear. Our ears can't pick them up. Now, other animals might be able to, and we'll talk about some examples later of animals that can actually hear below and then above. Anything above our hearing is called ultrasound. So anything above 20,000 hertz is an ultrasound. And we use these too. We use ultrasounds for imaging. And then a lot of animals use ultrasound for like finding prey. So bats and dolphins do this. And the sensation of a frequency is commonly referred to as the pitch. Pitch is simply a term musicians use to describe specific frequencies. A high pitch corresponds with a high frequency. The tuning fork is vibrating really fast. And a low frequency, a low pitch is a low frequency. As an example, this is a high pitch. It has a high frequency. When I tap the A, it vibrates faster per second, more vibrations per second, than, say, a low A. Okay? So we can hear all of these, right? but each one has a different pitch. Okay, pitches are simply just a specific frequency that musicians use and identify. Okay, there are literally every frequency has its own slight pitch. It's just that we have very specific ones that we use. Okay, it's just easier that way. And you can hear the difference between them when you tap them. And that doesn't work. I need another one of these. Let's see. I need something hard to hit it with. Can I borrow somebody's head? That's not going to work. Darn. Okay. I'll show you guys in a little bit. I've got some demos to do today as well. So the sensation of a frequency is just referred to as a pitch. It's what we hear. Okay? So if you hear a low note, that is a low frequency. It has fewer vibrations per second. A high pitch is going to be more vibrations per second. And we can change this in the human voice, which is really cool. The whole point of your vocal cords is so that you can change the tone of your pitch, otherwise you would sound very monotone. So, humans, we can hear from about 20 to 20,000. Do you guys remember the YouTube video I showed you where we listened to the different frequencies? Here, I'll show you what I mean. So that's the lowest frequency we can hear. Make sure this isn't. So as we increase the frequency, the pitch goes up. And what you're going to notice just keeps going up, right? So our frequency's getting bigger. What's happening to our wavelength? It's getting smaller, right? Because the speed doesn't change. And we're about to irritate the ever-living crap out of everybody around us. You can still hear it, right? Yeah. I'm gonna turn it down a little bit. It's starting to irritate. Can you still hear it, Mrs. Gates?
Yes. Noisy neighbors.
Uh-huh.
When it will be gone? Will it eventually go away?
I'm starting to lose it. I lost it. Can you guys still hear it?
I lost.
Yeah. There's a reason for that, by the way. The sound is still coming out of my speakers, but what's happening is our ears lose the capability of hearing higher and higher frequencies as we get older. And so, like, if we played this video for your parents, I guarantee some of them would have even lower numbers than Mrs. Gates and I. And the reason for that is damage is done in our ear over time, and we lose some of our capability of hearing some of those frequencies, particularly high frequencies. So if you're wearing, like, earbuds and you're listening to your music too loud, you're damaging your ears constantly. We're going to talk about that when we talk about intensity and decibel levels, because, like, man, having wonderful speakers is awesome until they start damaging your ears. Then it kind of sucks. So as we go from low frequency to high frequency, we go from a low tone to a high tone. And so tomorrow, hopefully if we have the computer set up, we're going to play around with telephone tones and a few other things using the verniers. And then next week, if we get to it, we might not. We'll probably start playing with resonance as well. So human perception continued. When two sounds with a frequency differ or have a difference that's greater than 7 hertz are played simultaneously, most people are capable of detecting the presence of complex wave pattern resulting from the interference and supposition of the two sound waves. So if it's more than 7 hertz difference, we can hear it. If it's less than 7 hertz, our brain is not capable of differentiating between the two sounds. And there are certain sounds, certain frequencies, when heard together, sound really nice. Okay? In music, we call these like octaves and thirds. They sound great together. We call them like a harmony. But we have to be careful with harmony because we're going to get into that later too in another class. So there are certain frequencies that just sound nice together. And so I actually have a demo of this where we can play around with two tones, right? Okay, so two different tones are playing at the same time, because if I change one, okay, we're in a Discord. That doesn't sound very nice, right? But if I take this and I take it down to 220, that's a much more pleasant sound, right? Those two waves are working together. Basically, one is filling in halfway between the other one. So your wavelengths are half as much as the other ones, which is pretty neat. Now, I'm going to stop both of them, and I'm going to set it. So we're at 440. If I set this at 435, or 436, and hit play, you hear that? We call that a beat. Okay? It's throwing you off, isn't it, a little bit? It's like, wait a minute. Our brain can hear the difference a little bit, but they're so similar that our brain can't quite differentiate between them, so it does this beating thing. Whereas, as we get closer, the beat goes away, right? Which is pretty neat. So our ears are really cool. They can hear different things. And this website's fun to play with because you open two of them and you just make some random sounds. Now, if two... Whoa. Okay, so this is called an octave. So 220 to 440. What do you think the next octave up is going to be? 660? 550? There could be any number of patterns, and we can play around with it. So we're going to stop both. At 550, so like going up by 110. Not quite. Because if they were an octave, they would sound really similar and they would kind of go together. If we went to, say, like, maybe it's 220, so 660. Nope, that's a harmony again, right? That doesn't sound so bad together. Instead, it's, what would a different relationship? 220 to 440, what might be our next one? Double it, right? So 880. This is going to be high, by the way. See how those two sounds go together? And they kind of fit together really nice? That's an octave. We'll play around with this a little bit more in a bit, because we're going to look at some other stuff as well. So, when we hear certain sounds together, they sound really, really nice. And it's not just octaves. We have like thirds. Thirds sound fantastic together. And that's where harmonies come from in music, where you have multiple different groups or instruments playing different notes together, and they sound really nice together. So, that brings us to octaves and thirds. I'm getting ahead of myself. So, such sound waves form the basis of intervals of music. So, for example, any two sounds whose frequencies make a 2-to-1 ratio are said to be separated by an octave. So, an octave might be C. Okay, that's an octave. They're separated by double the frequency. And they sound really nice. So two sound waves sound good when they're played together if one sound is twice the frequency of the other. Octaves sound great. Okay, when you're singing music, and I don't know how many of you guys are in choir or band, but like as a musician in high school, we talked a lot about like octaves and thirds and like what sounds nice together. Because some things don't sound good together. Some things are dissonant, where they don't click right. But other things are really pleasant. And there's a whole bunch of scientific research behind why these sound pleasant. Like, does it reverberate in our ears differently or something like that? And there's some research being done right now. It's all like music and physics go hand in hand. Because music is literally just looking at the physics of sound waves and what sounds nice. Now, similarly, two sounds with a frequency of a 5 to 4 are said to be separated by an interval of a third. Such sound waves are also good, or also sound good when played together. So to find a third, you just multiply the frequency by 5/4, so 1.25. So if I wanted to do the same thing with that website, where I'm playing the two different tones, I can easily find a third. Oops, that's not what I wanted. No, don't open up Firefox. Go away. Not now. Not now. What? Consistently, yes. Not at school, because it blocks it. All right, so let's set it at 220. Right? And we want to find out what the third of 220 is. Well, we take 220, and we multiply it by 1.25. We get 275. So this is a third. Okay, it takes a second, but that's considered a pleasant sound. Okay, as opposed to like not so pleasant of a sound. Okay, dissonance and harmony. So there are thirds, there are other steps that are really popular in music, and depending on the type of music. And the interesting thing is this is all based in frequency, and it sounds really nice to us, but our music and other country, like other music from other places, don't always follow the same systems. They still have the same frequencies, but like what sounds pleasant to us might be a little different somewhere else. Or the unpleasantness of some music. We call that like dissonance. And you find areas that have music that's really different. So other animals have different levels of hearing. They can hear different frequencies. So dogs, 50 to 4,500. And so keep in mind, we are 20 to 20,000. So dogs, they can't hear as low as we can, but they can hear higher than we can by about double the hertz. Cats have an even wider range than dogs. They can hear even higher pitches. So like a dog whistle is a whistle that we can't hear, but your dog can. It's a higher frequency. Bats being nocturnal, they create and rely on echolocation, and so they can use frequencies up to 120,000 hertz. And we're going to talk about like why in a minute. Dolphins can detect frequencies as high as 200,000 hertz. And elephants actually can detect frequencies as low as 5 hertz. So they can hear lower sounds than we can. And so, like, the demonstration shows voicing our voice, which is only 85 to 1100 hertz, but we can hear 20 to 20,000. A blackbird's is 2,000 to 13,000, but can hear 250 to 21,000. What's the evolutionary benefit for organisms to be able to hear better, hear a wider range than being able to vocalize that range? Why? What advantage is there to be able to hear pitches above and below your vocalization? If our vocalization is 85 to 1100, well, let's take a look at a cat. A cat's is 60 to 65,000. Their vocalization is 760 to 1520. Blackbirds 2,000 to 13,000, but they can hear from 250 to 21,000. Can they hear birds, or can blackbirds hear cats? If blackbirds can hear here and cats can talk here, can blackbirds hear cats? Yes. Why would that be an advantage? If you're a blackbird, why would it be an advantage to be able to hear a cat? Yeah, so you don't get eaten, right? So if you can hear much greater ranges, you're able to hear predators or prey. Okay, dolphins have a huge range. They can hear a ton of different range. Why? Because anything that vibrates gives off sound. Okay, when a fish is swimming through the water, is it vibrating the water? Absolutely. So it's giving off a sound. It might not be a sound we can hear, but a dolphin might be able to pick that up. Okay? So that's what we're talking about. When we talk about an evolutionary advantage of being able to hear much greater ranges, we're able to hear prey and predators, we're good. Okay? If you don't have anything that eats you and it's above a certain level, you're not going to need that hearing. Okay? So like the lizard, he has his own hearing. His hearing is better than his own vocalization, which is nothing. Okay, the lizard doesn't make any noise except for when he's really angry. Okay, but birds want to be able to hear cats, and probably dogs. When we talk about sound intensity, what we're talking about is the volume. So the amount of energy that is transported past a given area of the medium per unit of time is known as the intensity of the sound wave. The greater the amplitude, the greater the rate at which energy is transported through it, and the more intense that the sound wave is. So we put more energy into it, the amplitude of our wave gets much higher. So remember, that's how tall and how low our waves go. In a string wave, anyway. And when we measure intensity, which is the amount of volume sound has, we're going to measure it as the energy per time per area. Okay, and since energy divided by time is actually power, which we'll get into next semester a little bit, but for now we're just going to talk about it. Power being energy per area, energy per time. Like, what's an example of energy per time? Like, if you're paying an electrical bill, you're paying by the watt, okay? You guys probably aren't paying electrical bills yet. I pay my electrical bill. Otherwise, I turn my power off. So, watts per square area or meter squared. So when we look at an intensity measurement, we're talking about watts per area, okay, power per area. And we know, because we've talked about this already, as you get further and further away from a sound, the intensity decreases. Okay, and we can test that outside, no problem. I could be yelling from one side of the building, and you could be like walking away from me, and you're going to hear it less and less. And I can prove it to you because in a minute we're going to talk about decibels, which is how we kind of turn this into our hearing. But intensity, if I were to play a sound, let's pick a pleasant one so we're not bleeding from the ears. Sorry, speakers are really loud. Okay, so intensity. Now I'm going to do this in decibels. Decibels are not quite what we're talking about here. We're talking about watts per square area. Right next to the speaker is about 95, 90, 96 decibels, right? But as I walk further away, about 50. Yeah, see the decibels went up here, so I must be picking up a node and an antinode. We're going to talk about that when we play in the auditorium. But intensity should decrease. And like, if you're at a concert, the further away you are, the harder it is to hear the concert. So just leave that tone going all the time. Walk out the room on break. Leave it going for Mrs. Gates. All right. So intensity and distance. The mathematical relationship between intensity and distance is sometimes referred to as an inverse square relationship. So the intensity varies inversely with the square of the distance from the source. So if the distance from the source doubles, the intensity is quartered. So every time you double your distance, the intensity decreases by 4. And that makes sense, because if we think about sound, sound is coming out of my voice right now. As I do that, the waves are spreading themselves out. And as they do that, they spread further and further away. As they do that, they only have so much energy. And so that energy has to get passed out to a bigger and bigger area. And as it does that, the amplitude goes down. The energy goes down in that wave. So it would make sense that as it spreads out, and my voice doesn't spread out in one direction, right? It doesn't go right straight forward. It goes out not just in 180 degrees, it goes to 360, but also all the way around as a sphere. So if I was standing 10 feet in the air on like a ladder and I was talking, you'd still be able to hear me. My voice isn't in one plane. It goes in all directions. So as we spread out, it basically gets thinner and thinner. And if you think about it, you're like, well, I can still hear you, Mr. Schultz, even though I'm this further away. I'm putting out a lot of energy in my voice. But if I'm talking quieter, you start to lose it. Okay? So, intensity and distance. Now, we take intensity and we modify it to what we can hear. And we call this decibels. And you've probably heard of decibels. Okay? If you've ever gone to a rock concert or talked about like being at an airport or just in general, decibels are how we measure the sound and how loud something is compared to our own reference point. Okay? So the faintest sound that the typical human can hear or detect is an intensity of 10 to the negative 12 watts per meter squared. This corresponds to a sound that will displace air particles a mere 1/1000th of a centimeter. We can hear vibrations up to a billionth of a centimeter, so something that's vibrating really, really small. Okay, that's that really high frequency at a really small wavelength. The fastest sound that a human can detect is known as the threshold of hearing. Or the faintest, sorry, not fastest. That doesn't make sense. And decibels are going to be based on a logarithmic scale, so factors of 10, due to the really wide range we can hear. So we took what we can hear in terms of volume, and we adjusted it via a scale to make sure that we could fit it all in. And what that means, I'll talk about in a second. But here's an example of decibels. So loudness comparison. I gotta crank it. Technically, we can still hear 0 decibels. Space is 0 decibels. So the rustling of leaves is at about 10 decibels. So a whisper is at about 20. Your clock ticking on your wall is at 30. So it's not really much louder. Every time we go up, we're going up by a factor of 10. So bird songs are about 4,000 times louder than space. Or 1,000 times. Nope, 10,000 times louder than space.
I can't remember the last time that you invited me to your house for a cup of coffee.
So the cafeteria at lunchtime is about 70 decibels. Motorcycle is about 80, depending on the motorcycle. Jackhammer, it's 90, so 10 times louder than a motorcycle. Each of these is 10 times louder than the previous. We're in the threshold of pain, by the way, which is where your ears start to literally hurt. They'll start bleeding. Anything above that, and it'll kill you. Okay, so
dramatic music part of the
yeah, the eruption, yeah, it totally went off that way. So here's the thing: the threshold of hearing is 0 decibels. We'll take our break in a minute, okay? 0 decibels. 10 times louder than that is the rustling of leaves. So you could technically hear this, give or take. We all have slightly varying abilities in terms of hearing. So 10 decibels is 10 times louder than 0. 20 decibels is 100 times louder than 0. This is how a logarithmic scale works. It goes up by factors of 10. So 0 decibels is 10 to the 1, 10 times, 100 times, 1,000 times, 10,000 times, 100,000 times. And so our scale, because we can hear so many different ranges, is pretty impressive. Now, the threshold of pain is when our ears start to actually literally hurt. Okay? At 160 decibels, your eardrums, which are what sense the pressure waves, They're little thin. They're basically tiny little thin pieces of art. They're not quite skin, but like they're very similar. They pick up the vibrations. So like you can hear me talking right now. They're just vibrating as I talk, and probably getting bored. At this volume, at 160 decibels, your eardrums literally explode. They just shatter. They like pop. It's really bad. Like this will kill you. Okay, because basically you're creating a pressure wave that's going into your brain. You don't want that. The threshold of pain is basically where it starts to hurt. If you've ever gone to, how many of you guys have actually gone to like a loud rock concert? Anybody? Losers. Okay, Caden, who do you go to? Metallica? Metallica's loud. Okay, like they're known to be loud. There's other bands that are louder, but like they're pretty loud. When you got done, how did your ears feel?
Everything was really quiet.
Yeah. Your brain gets used to really loud noises, and they adjust to it. But it's also a little bit of damage, too, because when you go to a rock concert, your ears get a little damaged. And so the more concerts you go to, the more damage your ears get. If you ever watched a musician play live, they almost always have earbuds in. Either they have earplugs to block the sound out, or they'll have earbuds that are helping cancel some of the sound and volume. Because that way they're not destroying their ears. Because a proper musician doesn't want to be deaf by the time they're in their 30s, because then your music's going to sound really bad. So the loudness of sound is dependent on the listener. What's loud to one person might not be nearly as loud. And that has to do with the sensitivity of our eardrums. It also has to do with any damage you've done to your ears. So if you listen to earbuds every day at max for hours, you're going to have damaged eardrums. Because there are tiny little hairs and stuff inside of your ears that help pick up and control sound, and if those get damaged, we start to lose hearing. Okay, there's other things that cause loss of hearing as well. So this is decibels. And then the last thing we're going to talk about today before we go on our break is sound waves at different barriers. So this is what we talked about in our last unit, but I wanted to talk about it specifically dealing with sound. Sound can reflect in two different ways. There are what are called reverberations, and then there are echoes. In a reverberation, the reflected sound reaches the ear less than 0.1 seconds than the original sound. When we're in the classroom, the reason that anybody in the back row can still hear me is because of reverberation. What happens is my voice is carrying off, and it's going off, and it's going to hit the walls, right? And it's going to reflect off of the wall. Some of it gets absorbed. And as it reflects, it goes to your ears from different angles, which allows for more sound to travel through. If you're a sound designer for like a concert hall, reverberation is incredibly important because the sound coming off of the stage is bouncing off of all the walls. And if it bounces off and it comes together, it's going to interfere, right? Interference can be a good thing. It could increase your volume or it could decrease it. And that's why sometimes you go to a theater and there's a dead zone. And if you've ever gone to a movie and you've sat in a specific spot, and this has happened to me a couple of times. It happened to me when I went to see, what movie was it? It was Infinity Wars. The first time I saw it, I sat in a seat where I couldn't hear part of the movie because the reverberations, the reflections of the sound, hit just right where they canceled each other instead of increasing. And so I didn't hear parts of the movie because my seat was in a bad spot. If you're a good sound designer, your concert halls don't have these. They don't have dead spots. They only have full reverberation where you get nothing but good sound. And if it is a bad spot, they'll either like block that seat off or they'll design the theater so that there's not a seat there. An echo is if it's more than 0.1 seconds. And do you guys remember approximately what the speed of sound was? It's in your notes, right? The speed of sound is, yeah, pretty fast, right? Like 343? Does that sound right? Your notes are right in front of you. Yeah. 343? Yeah, 343. So if it's 0.1 seconds, that's 34.3 meters. So anything beyond about 100, 120 feet is going to give an echo. Okay? And in this case, it's traveling far enough that our ear can differentiate between the sound. So it can hear the original sound and it can hear the reflected sound. So that's what an echo is. The distance is far enough away that we can hear both the original and the reflected sound. Reverberations, we can't. Our brain just can't figure that out. Like, that's input that doesn't quite click correctly, and so we don't figure it out. Refraction is pretty rare in sound unless you have a change in temperature. And we see this best on a lake. So sound along water tends to bend towards the water due to the temperature differences. As you get closer to the water, it tends to be cooler. Okay, water has a high specific heat, which means it pulls heat into it really well. So if you're yelling along the edge of a water, along the edge of a lake, what happens is your voice, as it goes through the two different temperatures, one of them is going to start to bend downward. And as it does that, your voice tends to travel down towards the water. So if you're like trying to yell at somebody from across the lake, it's harder to hear. That's refraction. We don't see a ton of refraction with sound waves. Diffraction, however, is really easy to see because sound can bend around an object. So we talked about this on our test. If I'm talking out in the hallway, you can still hear me, right? That's because the sound waves are bending around the solid object. So as they do that, you can still hear them. Sound is really good at diffraction. And depending on who you are, you might use this as an animal. You might use this to your evolutionary benefit. Elephants and owls use really low wavelengths because they bend really easily. So owls and elephants use this to bend sound around different things. If you're an elephant living out on the Sahara, or the Sahara is a bad example because that's a desert. If you're out on the grasslands and you want to talk to an elephant that's like a mile or two away, if you use a low wavelength, a big wavelength, that wavelength can bend around things really easily. So that sound is going to travel around different objects really well and keep going. Whereas if you have a really small wavelength, things don't bend around really well. So if I were to talk in a low voice versus a high voice, you'll hear the low voice first. This is also why when you have somebody with a really loud stereo that lives in your neighborhood, you can hear their bass coming, right? Or, I don't know, who's got a really loud stereo in their car? Okay, we can hear you coming if you've got music blasting, but we only hear the bass. We never hear the treble. And the reason for that is bigger wavelength. Bigger wavelength bends. Smaller wavelengths don't. In fact, bats use ultrasonic, which have really, really small wavelengths because they don't bend. If you're a bat and you're flying through the air, right, and you're trying to hit a moth, you're trying to find food, you're going to chirp these ultrasonic sound waves. And as they hit the bat or the moth, instead of bending around it, which is what most of them do, it bounces right back. And then they have those big ears so they can pick up on that sound, and now they know where their food is. And then they can fly towards it. And they just keep doing this. Dolphins do the same thing. So smaller wavelengths don't bend. They bounce off, or they just keep going. And so bats don't have to worry about flying into things. Because if it bends around, it might bend around and then they can still hear it. So instead it bounces off or it doesn't. And now they know where to go. So pretty cool stuff. All right, that's it for the notes today. Let's take our break. That's a lot.